Today my topic is using ultra-fast spectroscopy to understand the relaxation dynamics in the metal nanostructure. Before I start my talk, I would like to acknowledge my advisors, collaborator, and the people who I have been working with, and also funding agencies. Ken Appenberger, who is right now the group, is in Penn State, and Stephen Link and Christy Landis, I learned a lot from the microscope knowledge from them. Peter Norander and Naomi Halas gave me a lot of help and advices on not only science but also career paths. Yong Chaojing and Chris Arterson, who provided very high quality samples in the nanocluster project. John Setter is theoretical physicist who can help me to modeling the acoustic vibrations. And also last, I will thank all these funding agency providing enough money for me to do this ultra fast measurements. Before I start my talk, this is outline what I'm talking about today. First one, I want to introduce metal nanostructures, especially gold nanoparticles. There are two different types of nanostructures. They have completely different applications. So one is called nanocluster with atomic position. The second one is called plasmonic nanostructures. If I want to understand relaxation dynamics, I have to use pump rule measurement, which I will also call it transient absorption spectroscopy, to understand this ultra-fast process. By doing so, we can answer two important scientific questions. The first one is, what is the smallest nanoparticle which support the surface plasma, or they still have free electrons? The second one is, what is the acoustic vibration properties in single particle measurement? First one, let me talk about the metal structures. The bulk materials, I think everybody very familiar about their properties. The color is shining, the electron conductivity, because of the very good electron conductivity is very good, so they can be used for you because of electron is free to move, so the electron conductivity is very good. This property is independent on the shape or size of bulk metal materials. However, when the size of the nanomaterial shrinking into a nanometer scale, we find a lot of properties is strongly dependent on the size. The first one, as what I will see from the picture, we have four different nanostructures of metal gold, and their structure is slightly different. Also, their size is slightly different. But we see their optical responses is totally different. They cover the whole range of the visible range. All this tunability of colors or optical responses is because of there is strong light matter interactions between metal and light and photons. These light matter interactions give us a very unique phenomenon called surface plasma resonance. It is very easy to understand surface plasma when you have a nanostructure electron is free to move inside of the particle. We use photons to exciting the nanoparticle, and the electrons will collectively oscillated, or it will be collective oscillations. They will generating collective oscillations of electron shit. When you're using photons to exciting a nanoparticle, we will generate collective electron oscillations on the surface of nanostructure. When the nanoparticle becoming bigger, this surface plasma energy will shift into red. In this case, we can control the energy of surface plasma resonance. In the future, a lot of applications based on this phenomenon. The first one is called scatter light, because when we change the size of structure, they are responsive to have different optical responses. We can use that for bioimaging, because this near infrared coupling between your nanoparticle and your environment, we are developed this surface enhanced Raman spectroscopy. Recently, hot electron generations has been considered as most critical effect uh, to change the efficiency of the solar cells. Because when you're emitting so much energy into the nanoparticle, your electrons getting hot, and can improve that. If we understand relaxation dynamics of hot electrons, we can improve the solar cells. But all of these applications, I think they're very useful, and a lot of people are studying it because we can manipulate that easily by changing the size of nanostructures. But when we are thinking about the size effect in the nanoparticle, we have to think about a little bit deeply. For example, if we only making the nanoparticle smaller and smaller until we only have one atom gold, I'm pretty sure there's no plasmonic behavior because electron is not free to move. They have energy gap is not continuous anymore. Instead, if we only have few atoms of gold, put them together, they still do not supporting surface plasma because it's acting like a molecular system. The dominating effect is called quantum confinement. So at this moment, we are talking about two different species of nanoparticle. The first one is electron is free to move with generating surface plasma. It is collective oscillations of electrons. When we are using light to exciting a nanoparticle, we are calling it a multi-electron excitations. But in the molecular system, when you're exciting on the photons on the molecular, we only generate single electron from ground state to the excited states. So two different species, they have totally two different excitation mechanism. This ultra small nanocluster with atomic position in 2008 has been prepared has been transferred from gas phase into the solution phase, but they found out this solution phase gold nanocluster is very stable and also very active in this photocatalysis results. However, the relaxation, however, there is one fundamental question which has not been answered. For example, where is the onset between these two different nanoparticles? And in another word, what is the smallest nanostructure which is still supporting surface plasma? Second question is, what is the differences between the dynamics? Remember, the dynamics of hot electrons in golden nanoparticle is important because we want to use it in solar cells. But for the small nanocluster, we want to understand relaxation dynamics because it provides a lot of fundamental mechanism in this photocatalysis results. That's why we have to understand the relaxation dynamics ultra-fast process because all this process happened in a picosecond or nanosecond level. So what I have built is using femtosecond transient absorption spectroscopy to look at the relaxation dynamics. I think it's very important for us to understand what is pump rule measurements. For example, if we have a three-level system as a molecular, the molecular will stay at a ground state usually. According to the Beer's law, the absorption intensity is strongly dependent on the population of molecules stay on the ground state, or in another word, concentration. When we are using an ultra-fast laser pulse to exciting the molecule, what happens is partial of the molecule will absorb the photons and be excited into the excited states. After excitations, because the population of molecules stay on the ground state are decreasing, then the absorbance will decrease. However, we're creating a second channel between the two different excited states. Here, that's why we have a second peak as I plotted in the red curve. Then what we can do is we can plot the differential absorbance before your excitation and after your excitation versus the wavelengths. We can get a very typical transient absorption spectrum. For example, the negative peak we call is ground state bleach because it's monitors the transition between the excited states and ground state. The positive peak I call it excited states absorption because that's the transitions between two different excited states. And then furthermore, we can monitoring or we can change the pump and probe time delay, and then we can recording how fast this ground state bleach returns back to zero. These are telling us how fast these excited molecules returns back to the ground state. These are telling us what is the lifetime of excited states molecule. By doing this ultra-fast spectroscopy, we can look at the relaxation dynamics. I have demonstrated that. The next one I want to understand or summarize is what's the relaxation dynamic in a metal nanostructure which support this surface plasma resonance. So Greer Harlan have done a very good job to summarize. He just put these nanostructures into the transient absorption, look at relaxation dynamics. The first one is called plasmon dephasing. The plasma is damping very fast. Your lifetime is only 50 femtosecond or 30 femtosecond in this range. The second one is after the energy damping from the plasma transfer into the electrons, we are generating very hot electrons. This is called hot electron generations. This is also very fast, below 100 femtosecond. The third process is called electron phonon coupling time. This means when your electron is extremely hot, for example 3000 K or 4000 K, however your gold nanoparticle which is phonons remains at room temperature. At this moment, the energy will flow from high temperature electron gas into this low temperature. This process is called electron phonon coupling time. The third one is the nanoparticle becoming hot. They will dissipate their energy into the environment, but they will launch another very unique property called acoustic vibration because of these coherent oscillations of phonons. Today's talk, I will only cover this electron-phonon coupling time and energy dissipation environment process because my ultra-fast laser is only 80 femtosecond time resolution. It is very hard to resolve these two dynamics, but there is a way we can measure it, but I'm not talking about it today. Let's look at the transient absorption spectra of a golden nanoparticle where they have surface plasma resonance at 600 nanometers. What we saw here is if we look at relaxation dynamics kinetic trace, where we saw that at least there are two exponential decay or two decay components. There's a fast component and a slow component, which belongs to the electron-phonon coupling time and also the energy dissipations. One of the interesting phenomena we are looking at is when we are increase our laser power. By doing so, we are increase our excitation pulse energy. By doing so, we can increase the electron temperature into higher temperature. Then two temperature mode are predicting is the energy transfer from high temperature electron gas will transfer into the phonons. The coupling time will be longer. That's why when we are increase the excitation energies, the relaxation time of electron-phonon coupling will have this linearly dependence. We can use this method to identify which this nanoparticle is a plasmonic or not. For example, in a molecular system, usually we do not see this excitation energy dependent because we only create a single electron transition. There's no temperature differences. By doing so, there is no electron-phonon coupling time usually in this molecular system. My collaborator had prepared very good high quality sample about ranging from 1.3 nanometer up to 13 nanometer. What we saw on 13 golden nanoparticle, we saw a very strong surface plasmonic band. However, when the size becoming smaller and smaller, we find out this plasmonic band gradually disappeared. This picture are telling us the onset between plasmonic and non-plasmonic appears between 1.3 nanometer and 2.5. We put all these nanostructures into this transient absorption spectrum. What we found out is gold 144 with 1.8 nanometer as a size is the smallest nanostructure have this linearly dependent on your excitation energy. So it is the first time we characterize what is the electron-phonon coupling time. It is remember, for example, gold 102, which is a molecular, and molecular systems, their coupling time, single electron excitations do not generate this electron-phonon coupling time. That's why the relaxation time is independent on our excitations. So this topic to identify this gold 144 has been a very hot topic because people are trying to do is they start slightly modification their structure, for example, changing the ligand, doping some different materials into the gold 144, and people are trying to do is there any possible we can manipulate these behaviors from mechanical properties into non-mechanic. So has been a very hot topic in the past 3 to 4 years, but we are very happy is we are opening this subject to this whole society. A lot of people are following this work. But for me, as a spectroscopy, what I want to, as a people who are working on the spectroscopy, I want to build up the full relaxation map in this gold 144. So this is a transient absorption spectra in gold 144. What we saw here is we saw a very congested spectra. A ground state bleach centered at 520 nanometer sounds like a plasmonic resonance, and also they have a broadband excited states absorption. So it is a spectral or an energy domain. They are strongly overlap, but on the time domain, they are also very overlap because each component damping very fast. It is only a few picosecond, then all the signal is gone. The second part, then we have to using a little bit special method to analyze the data. The data I call it here is global analysis. By decompose the three-dimensional spectra into a few different components, we found out three different components, and we can study this component independently to look at relaxation dynamics. The first part is ground state bleach, which is negative, centered at 525 nanometer. We found out this component lifetime linearly dependent on your excitation energy as what I have just described. It shows it have a plasmonic in the nanostructure. But to distinguish it from the surface plasma, because the crystal structure of gold 144 is slightly different, they have 114 atoms as a core. They have a gold and thiol unit as a shear. This is co-shear structure. On the shear is a ligand structure. They are not supporting surface plasma. Only in the center, only in the core is a surface plasma resonance. We name it as co-localized co-localized plasma resonance to distinguish with it from the typical or traditional surface plasma resonance. But component two, I think, is more interesting because we found out there is another important process. I give another evidence about the metal or free electron behaviors or metal behaviors. The component two is broadband excited states absorption. We find out their lifetimes is quadratically dependent on their oxidation state. This is very interesting because another quadratic equation found in metal sphere is charging behaviors of metal spheres. What is happening here, if we have a metal sphere, doesn't have to be nanoparticle, we remove the first electron, need very little energy, but if we remove the second electrons, we need more energy. If we keep removing the electrons from the nanoparticle, the energy required to do that so is increasing. The equations between the energy and also your charge is a quadratic equation. For here, the case is we believe is when we change the oxidation state, we are charged the nanospheres inside of the core. By doing so, we are opening the energy gaps between the excited states. In this case, our relaxation time between the excited states have similar behavior. This is providing a very side evidence on the metal behaviors, but components 3 are telling us a different story. We found some molecular behaviors. For example, the component 3 is a very weak, but its negative peak around 670 nanometer. What we found out is it might be a stimuli emission, but because their excited dynamics, stimuli emission is very easy to understand. Is when we have a two energy level system, electron at excited states. When one electron is passing by this system, the electrons will relax back to the ground state to emitting a second phonon. That's why transient absorption, the stimuli emission is always negative. Then what we saw here is when you have integrate steam emission is very common in this metal to ligand charge transfer process or charge transfer state. However, in order to prove there is a charge transfer state, we have to put this molecule into different solvent to look at it because polar solvents around in this charge transfer state will stabilize this charge transfer state and make the energy gap is closer. So what we saw here is by changing the dielectric constants of the solvent, we saw when we have a polar solvent, the emission energy are shifting to the red, which makes sense because energy gap is closed. Also, the intensity are increasing because it's stabilized, so intensity is larger. This is only special information, but on the on the dynamic information telling us the same story. When the energy gap is closed, the relaxation time in THF is much slower or much faster than the toluene. Both of these information are telling us there is a charge transfer state in the gold 144 system because on the ligand share, they have a gold and metal structure. They have metal and ligand structure. They have charge transfer state. This process can be changed by the solvent. So I think 144 is interesting. People can do a lot of chemistry inside because they have these two systems. Most of dynamics is dominated by plasma, but partial of this dynamics is dominated by charge transfer state. That's why this is a very interesting system, and we do open these topics for the society. After we understand, but for me, as a people who working on the spectroscopy, if I want to understand the nanocluster, we do not want to understand plasmonic because we want to understand for the smaller cluster what is property because we know smaller cluster is very active for photocatalysis. So I pick up one of the nanocluster to keep study this state resolved dynamics. We found out the first one is for this nanocluster, they have co-shear structure. Inside of a core is a gold 13, outside is a gold and ligand thiol, very similar as gold 144, but it is small enough which do not support surface plasma. We found out is if we are using 400 nanometer to exciting the nanoparticle, this nanostructure, we found out their relaxation dynamics is dependent on your solvent, which is the same idea in gold 144. We have a charge transfer state. According to the simulations my collaborators have done, they have a ligand band on the bottom, the gold band, which is super atom D, belongs to the gold core. This is excitation by using 400 nanometer is called interband excitations. We are pumping electrons from the ligand band into this gold band. That's why they have a charge transfer state, and this relaxation is assisted by charge transfer. However, if we're using low photon energies to exciting nanoparticle, which only promote electrons from the gold band P into the gold band D, by doing that, we do not see any solvent dependence. Instead, we saw very interesting systems called vibrational coherence. This vibrational coherence, if we're detecting a different wavelengths, we find that there's a pi phase shift. Because can be explained by the Frank Condon curve. For example, we promote electrons from ground state into excited state. Electrons will be we're generating this superposition of electrons at excited states. When we're probing different channels, they will have vibrations on these two different probing channels and also have this pi phase shift. This is like a stimulated Raman spectroscopy. That's people are doing this, but it's the first time we observe this vibrational coherence in the gold nano cluster. That's why we build up a second story. Is when we use intraband excitations, what we saw is a phonon-assisted relaxation. Why does this state resolve dynamic is important? Why is this state important? Why this one information are important? Because think about the photocatalysis. If we are using low energy photons to generating carriers inside of a gold band, we found their catalysis efficiency is very high, which means the gold metals, phonons, are helping this catalysis. If we are using a higher energy photons to exciting nanoparticle, we find the catalysis efficiency is very high, which means the ligand band is playing a very big effect in this catalysis reaction. So as a physical chemist, I'm trying to providing a lot of fundamental informations for the other chemists who can help their research and do their chemistry as a physical chemist, but we love this nanocluster for completely different reasons. Previously, I talked about they have so many these applications, you can use it for that device. But for physical chemist, we understand that because we love its atomic positions. Remember, this is purely gold nanoparticle, okay, nanocluster. Between the cluster to cluster, they are identical. They have same numbers of gold. They have same numbers of ligand. The structure is the same. When we are marrying their property, we can easily correlate your structure with their property easily and accurately. However, for if we're talking about nanoparticle, which supporting plasmonic, for example, here is a TEM image on gold nanoparticle. We find out is their size is slightly different. Their size are slightly different. Their shape is slightly different, and also their environment surface condition are slightly different. By doing that, when we are collecting ensemble measurements, we are collecting the average signal of all these nanoparticles, which is not accurate. For example, right now, if we have one person, for example, we have one person who are extremely rich sitting in this room, and then what's the salary? We have Tiger Woods sitting in this classroom. What's the average salary in this room is maybe $500,000 or 300K or 400K, but that doesn't mean everybody are making 300K because we have buyers, right? That's why a statistics class are telling us average number is not accurate. What we have to do in this understand the plasmonic particle, what we have to do is we pick up a single particle, characterize their property, and characterize their structure, correlated their property with structure. That's an accurate way to do. Let me give you an example about single particle measurement. For example, this is golden nanorod. It's a very good distribution. Size distribution is very narrow. The red curve is the ensemble measurement of extinction spectra. The black curve is the single particle measurement on the extinction spectra. We found there is a strong shift, and also we are underestimate their bandwidth. Okay, so this is a very good examples about single particle measurement is what we need to accurately determine their property. The next question is if I want to accurately understand the plasmonic dynamics, what we should do. So people are saying we have to combine. What I have done in RISE is build up this transient microscope by combining ultrafast spectroscopy with a single particle microscope together. I'm not the first person to build up this instrument. We are a lot of pioneer. Two of them are Michel Ray and Greg Holland. This is how they set up their experiment. The titanium sapphire laser is about generating 800 nanometers, and then it focuses the light on the single particle by second harmonic generation to generate 400 nanometer, and then we detect as pump light, the probe light is 800 nanometers. However, there's some limitations in this instrument is we cannot tunable their wavelengths. Remember, a plasmonic nanoparticle, when you change the size, your plasmon wavelengths shifting to different wavelengths. So when you only have 800 nanometer as detection, we are limiting your detection range. A lot of interesting system we cannot study. What I have done is I incorporate this super continuum generation white light fibers into the whole systems to generating a very stable white light ranging from visible range into the near infrared. It is not a very easy job because if we are generating super continuum generation, your laser pulse energy should be higher enough. But in a single particle measurement, when there's a trade-off, if you have very high lasers, you will destroy the sample very easily. So I have using this system, I developing these systems, we've optimized the whole system, which can help us to activate this single particle wavelength tunable transient microscope. There are a lot of advantages. First one is we focus on single particle accurate determinations. Second one, we do not amplify. That's the key part. We do not destroy the samples. Our pulse energy remains very low. Third one is their time resolutions, which is about 100 frame a second, still very good. And also I provided spatial resolutions, which is about 300 nanometers. It's still a microscope. Third one, I have tunability on the wavelengths. By using the ultra-fast microscope, what I want to understand is acoustic vibrations. I think everybody have done this experience when you are everybody are in high school, which is turning fork. Is when we have a turning fork, we use a hammer to hitting on the fork, while the fork was starting to vibrate. This is called acoustic vibrations. Our planet have these acoustic vibrations. It is driven by the earthquake. But what is hammer to how we can launch acoustic vibrations? We cannot use a hammer to hitting on the particle, will destroy it, and we cannot hit. The method I'm calling to is using ultra fast laser. Remember, after electron phonon coupling, we are injecting a lot of energy into the nanoparticle in a very short amount of time. At this time, the nanoparticle becoming hot very rapidly and expansion very rapidly. That's the hammer. Ultrafast is our hammer to launch this acoustic vibration. The second question is how we can detecting it. So we are employing the ideas in the optomechanics and how we detecting the gravity wave last year. I think everybody are very excited in science world, very excited about this news about gravity wave last year. So what they are saying is when the gravity wave is passing through our planet, there is small change of our planet. But how we detect these small changes? What we do is we put two big optical arms. Between these arms, there are two mirrors, and then the lasers is reflection between each other. If there are small changes on our planet, which will have a small change on this distance between two different arms, then what is happening here, their interferometry will change. So how we are measuring the mechanical changes, we are using opticals to measure these small changes. This is called optomechanics. In the nanoparticle, we can employ the same idea. For example, when the nanoparticle becoming larger or smaller, this structure will shift their surface plasmon resonance because electron density is changed, size is changed. For example, the nanoparticle becoming bigger, the plasmonic will shift into red. When nanoparticle becoming smaller, shrinking smaller, the plasma energy will shift into blue. By monitoring the optical responses at different time, we can find their acoustic vibration frequency and also the damping time. For example, I plotted this transient absorption, single particle transient absorption kinetics. What we saw here is a fast decay. This is electron phonon coupling time. I've spent a lot of time on it today, and also we have we observe these collective oscillations of the nano signals. This oscillation is because of this acoustic vibrations. The frequency in a single nanoparticle is about 10 gigahertz. Then we are trying to understand acoustic properties in nanostructures prepared by electron beam lithography. What we saw here is when you have bigger nanoparticle, the acoustic vibration are smaller. This is very easy to understand because frequency is determined by the speed of sound and the diameter. However, our simulation have some offset to predict our experiment method. What is happening is because in electron beam lithography, to make the nanoparticle is not sitting in a vacuum, instead it is sitting on the substrate, usually is a glass. And there is adhesion layers which makes it introduce some coupling between the nanoparticle and our substrate. So when you're exciting on nanoparticles, nanoparticle doesn't shift into other places. So this is called coupling with substrate, and it will result some shifting between your experiment and also results. But I'm interested is in the electron beam lithography. This mechanical energy will relax into the environment. My question is how fast this mechanical energy can relax to the environment. So what I have been using is describe the quality factor using quality factor to determine the damping mechanism. First one is I change the size, right? Because bigger nanoparticle, they have strong coupling with nanostructure. The energy flow from top to the bottom will be faster, which is predicted in our simulation. However, in our experiment, we saw a different result. No matter how I change the size, no matter how I change the substrate material, no matter how I change the adhesion or the coupling strength, the quality factor of this electron beam lithography nanoparticle quality factor is always around 10, which is also underestimate, much smaller than our simulations. These are telling us the energy flow from top materials into the substrate is not efficient. There is another dominant effect which is because of this intrinsic damping. So what I have done is I prepare electron beam nanorod and also synthesize this gold nanorod. This gold nanorod actually they have a single crystal, so a perfect there's no crystal defects inside of nanoparticle, but the polycrystallized prepared electron beam lithography prepared this polycrystallized. We found out their damping time is significantly different. These are telling us the intrinsic damping introduced by the internal defects is the dominant effect. Okay, this is a project I'm talking about single nanoparticle, but what I really want to understand is the acoustic vibration coupling between the particles. Because we already know when we have two particles sitting together, when they have the plasma will couple with each other. Peter and Naomi built a very beautiful model using hybridization models to understand the coupling strengths. When the structure becoming more and more complicated, for example, when you have auto rings and a central disk, they have generated this final resonance optical responses. This is all can be described by hybridization model, but my next question is when the particles sitting with each other, is there any possible they were starting to vibration and then they can change the acoustic vibration, which means they have coupling between each other. So what I did is I fabricated this three different structure. So we have a central disk, a larger nano disk, 100, 200 nanometer, and the outer ring, each particle is about 80 nanometer. And then I put the central disk into the nanoparticle. What we saw here is their acoustic vibration frequency have a very strong shift, belongs to the outer ring mode. For example, without any coupling, the frequency is about 21 gigahertz. But getting into 25 gigahertz, they shift about 35 gigahertz without changing any size. So this telling us there must be a something coupling between each other, but it's not plasmonic because uh, plasmonic lifetime is very short, right? So what I have understand plasmonic coupling need a medium because it's electron and electron interactions between each other, but photon-photon interactions need a medium because they are transportations. What I have been studied is if we have nanoparticles sitting on the surface of substrate, nanoparticle vibration will generate this surface acoustic wave, and this surface acoustic wave will feedback into the small nanostructure and eventually coupled. To prove this idea, when we change the substrate, the coupling strength is strongly dependent on that. So if it's a surface acoustic wave, there's another evidence we can do is we can separate this nanoparticle because when you're generating surface acoustic wave, this acoustic wave it will propagate, but eventually will disappear. So when we increase the distance between the particles, we found out the relaxation, their coupling strength is smaller, which is shown as the acoustic vibration frequency of the outer ring becoming smaller and smaller. So this is giving a conclusion said the mechanical coupling between nanoparticles is assisted by the photon propagation, which is dependent on the size. Then here is a we also need to build up mathematical models to predict this coupling. Here is what I've plotted is a frequency versus our gap size. We find it is perfectly linearly dependent. I will show why later. And then what we found out if it's a surface acoustic wave on substrate, the propagation is strongly dependent on the frequency. If we change the size of central disk, we are changing the frequency of the central disk, and then we are changing the frequency of the surface acoustic wave. We found out this trend which does match our prediction. So here we can see our mathematical model, which is using coupled oscillator model. When there's no coupling, the two fundamental modes, when they are coupled, one mode was shifting to high frequency, one mode shifting to low frequency. And the coupling strength is strongly dependent on two things, your initial frequency of surface acoustic wave and also traveling distance. So here we are the first person who observe not only plasmonic coupled with each other, but these acoustic vibrations will couple with each other. We do provide street evidence about that, and also we build up models to predict the coupling strength. So today I think I can have enough time to summarize what I'm talking about. The first one, we use ultrafast spectroscopy to characterize the dynamics. We found out it is very interesting because we can know uh, we can have state resolved dynamics. We also answer this question, what is smallest nanoparticle supported plasma? Second one, in order to remove heterogeneity, we are studying the single particle ultrafast spectroscopy. These are telling us the vibration in the plasmonic particle can strongly coupled with each other. The third one is if I only pump through measurement as an ultrafast spectroscopy, they are not only limited on that. There are a lot of different techniques. For example, magneto-optical spectroscopy. We put our cluster into a strong magnetic field, which is about 25 Tesla, and we see there we are looking at the spin dynamics and emissive state. And also we have a helicity resolve. We use cyclically polarized light or linearly polarized light to exciting this spin optical coupling. Also, we have using this two-dimensional electronic spectroscopy where we pump the light and probe the light with white light. By doing so, we can characterize the axion dynamics and charge transfer in the quantum dots. This is I have spent a lot of years to making this to make synthesize this cadmium selenide, cadmium sulfur. I think it looks very beautiful. For here, I also spend a lot of time to collaborate with different people. For example, I have involved a lot of projects including two-dimensional materials, solar cells, and so on. 哎呦妈，累死！